All right, so we had some questions on number 2, which I definitely think is a tricky one. It's a conceptual one, which I think are always the harder ones. And so in this problem here, we've got two charges, a positive Q and a negative 2Q. And we want to find out, is it possible for us to add another positive Q somewhere on the y-axis such that we don't change the total potential energy of the system? And so, again, lots of ways to think about conceptual problems, but the way I'm going to kind of try to talk about this is using two of our equations that we used in lecture so far, talking about electric potential. So the first one is the electric potential energy, which is U, is going to equal charge times the electric potential. And then another one that we used that we'll reference a little bit is that the change in the potential energy is the negative of the work done by C, where C stands for the conservative force. So here, the electric force is a conservative force. And the way I'm going to try to think about this one is by adding a positive charge. What I'm basically doing is I'm taking some positive Q that's really, really far away, like over here, and I'm taking it and I'm moving it to some point over here. And so let's just try to think about that for a second, okay? And one good way to think about this is to kind of split these guys up. And so let's just think, okay, let's imagine that the negative 2Q is not there. All right, and so if I move a positive Q in here towards a positive Q, hopefully you can reason that that would be increasing the potential energy, right? If I put these two positive Q's together, they really don't want to be next to each other, and so I'm increasing the potential energy of the system if you only think about that positive, right? And so our equation here says, right, so if I bring this guy in, the positive Q, the force between the positive Q's would be a repulsive force. So the force of electricity, of our conservative force, would be against it. And so the work done would be negative. And so it'd be negative, negative, and so we'd get an increase in our potential energy. And so that's just thinking about the positive Q. Now, if I think about the negative 2Q, right, the opposite thing happens. And so let's think about that now. So let's do this sort of over again. So now I'm moving the same thing in, but now we're just imagining that this guy isn't here, and it's the negative 2Q, right? And the force between those two guys is going to be attractive. And so as I'm moving this charge in, the conservative force is doing positive work. And so I get a negative times a positive. And in that case, the work is negative. Or I'm sorry, the change in the potential energy is negative. These two things, the positive Q and the negative 2Q, want to be together. So as I bring them closer together, I'm decreasing the potential energy of the system. And the analogy we always use is gravity, right? And so like if I lift the book up, right? If I lift it up, I'm increasing the potential energy of my book. If I lower my book, I'm decreasing the potential energy. And so here, because there is in fact two different charges, right, I've got sort of both effects. Okay, as I move this charge into this region, it's a positive Q, so the other positive Q, that one, again, is going to be doing negative work, okay, which is going to be increasing the potential energy, and then the other guy is going to be doing positive work, which is decreasing the potential energy. So just by looking at that, we can kind of see that, okay, we can reason that it is possible that those two effects could totally cancel out. All right, and so it's essentially, when I move it to the, in here with the positive Q, I'm increasing the potential energy. With the negative 2Q, I'm decreasing, and it's possible that they'll both cancel out so that the changes are zero. And so the real key then to sort of try to quantify this would be to take this equation. So the change in my potential energy is Q times my change in the electric potential. And we've used this equation in the videos and lectures a few times. Generally how we do this is we think about the Q as being the one that's moving and the delta V as being caused by the static charges. All right, and so if we move this one over here, so this is going to be kind of our key equation. Now, so my Q is just this guy, so it's my positive Q, that's the one I'm moving, and then the potential is caused by the static forces. Now, since the charge isn't there initially, then the initial potential is zero. The way I think about this is when we're doing this problem, we're starting it really, really far away, so like a distance r of close to infinity, so when you do that equation, it basically turns into zero. And so what this works out to be then is my change in my potential energy is going to be Q of the charge that's moving times the final electric potential. And so what this basically boils down to is it possible for the electric potential to be zero in some region on the y-axis? And so in this case, it turns out that yes, it is possible, and it'll happen at 2 places on that axis. And so let's just, we'll put that off for a second. And so again, basically what's happening is because there's 2 charges, one wants this positive to be there, one doesn't, and so we can work out a way that those 2 sort of things exactly cancel. And so then, just to find out exactly where those positions are, you can look at the solutions to do that. But basically, when we find the electric potential, right, what we do is we just take our equation for a point charge electric potential. So there'd be KQ, I'll call it R1, as in the distance from this charge. This would be, I'll call this charge 1, and this one charge 2. And then I'm going to add in negative K times 2Q over R2. And so this would be sort of the general formula for finding where this could equal 0. And again, I want this to equal 0. So what you can do is you'll be able to find 2 points. There's basically 1 point above here and 1 point below. So the way this works is because you've got this 2Q in the upstairs part here, right? Then what happens is you want to find a place where you're closer to the Q than you are to the 2Q. And so you can pick a point here. I should make this a little bit more clear that this one is actually, so there's a point in here where you're closer to the positive Q than you are to the negative 2Q, and those 2 cancel out to be 0. And then there's a point over here that you can find that will do the same thing. And so you can sort of take this equation here and set this up. And we did this a little bit, with electric fields. Now with electric potential, it's easier in the fact that we're not using vectors, but we're so used to vectors that's a little bit tricky. But you'll find there's actually 2 points there where that electric potential can cancel out. All right, hope this helps. Let us know if you have any more questions.